All right, so what we were doing at the end of last time was setting up the path integral functional methods. And there was an integral that we had there, which is the integral dx1 up to dxn e to the I 1/2 x dot a dot x. So that means summed over all the indices there, the dots. We make a summation. Plus j dot x. Again, the summation involved. And that equals 2 pi I to the nth over the determinant of a to the 1/2 e to the minus I over 2 j dot a minus 1 dot j. Okay, so we did this by first diagonalizing a, in which case it factorizes, and then at the end undiagonalizing it back to the original a. So that's for any a, this is true. That's your basic formula for functional methods. It's the basic Gaussian integral, and we'll use that today and the rest of the semester, to be honest. Let's do a test calculation, so warm up. So let's imagine I wanted to calculate using that a, the average value of xi xj, which is defined to be these dx's. I'll just put brackets around it. That's the sum of all of them. E to the minus e to the I over 2 x dot a dot x, but then we put xi xj there, and we divide by this thing without the xi's. So given this weighting, we want that. So there's no j in that. But if you temporarily give it a j, and you go up to this form up here, you can get this xi and xj by differentiating with respect to j sub I. So this is minus the, let's leave a little blank there, then it's the derivative with respect to j sub I, the derivative with respect to j sub j. So there's, in this sum, there's i's and j's somewhere, and differentiate respect to one or the other of z of j, and then you're going to set at the end of that j is equal to 0. Okay. That will give you the numerator, and the denominator is just gotten by setting the z of 0. You just set that j is equal to 0 anyhow, you get the denominator. Okay. So that's what you'd want. And so now, if we were actually to do these integrals, it's not terribly hard to do, I guess. But given a general matrix A, it looks hard to do. And so but it's pretty easy to take the derivatives of that. If I take the derivative with respect to j, I bring down an a minus 1. So if I take, this is then minus 1 over z of 0. Let me take one derivative first. So I've still got one derivative left over. This would give me minus I a minus 1 IL JL, so it sums over L, e to the minus I over 2 J dot A minus 1 J. Okay, so I've taken one derivative up here. There's two places J could be carry the label I. It's either in this sum or that sum, so I got rid of the factor of 2. And I have that minus I there. And then the last thing, I now have to take another derivative. Everyone see that derivative? Okay. Last derivative to take is I can take J on here, or derivative of J on there. However, you can see if I take the derivative on these guys here and then set J is equal to 0 like I'm supposed to, that it's going to vanish. This J right there is going to cancel, or drop everything out. So the only one you have to do is you take this derivative and you forget that guy. And so I get I a minus 1 ij is my answer. And that's where I get to. Okay. Likewise, maybe I shouldn't spend time doing it, but if I wanted to take the average of xi, xj, xk, xl, that would be, delta to the 4th over, 1 over z0, delta to the 4th of delta j, ji, delta jj, delta jk, delta jl of z, j, then set j is equal to 0 at the end. And if you do that, let's not do it. But basically it's the same thing. You bring down the various powers of a minus 1, but now I've got 4 derivatives to do. This turns into I a minus 1 ij, I a minus 1 kl plus permutations, which is a minus 1 ik j l il Okay, so I think I have all the indices right there. It's basically all the different permutations, but you bring down this factor. Okay, so just as a preview, when we get to quantum field theory, remember the transitions from quantum mechanics to quantum field theory is we take these xi's and replace them by phi's of x's. The integrals over dx's are going to be replaced by the integrals over d5's. So the I index is like x there. And the interesting things are going to be, I have where I had e to the I over 2 x dot a dot x. That's going to turn into something that looks like e to the I integral d4x. That'll be 1/2 phi box plus m squared, del squared plus m squared, phi, which is like the Lagrangian, and the equivalent things that look like xi's, xj's in this calculation here, going to turn into phi of x and phi of x prime. So two different locations, just like the two i's and j's. And that's going to turn into the Feynman propagator. That's where all field theory is going to come in. After I grind away for a little bit, we're going to get things like Feynman propagators, out loops, vertices, the whole shebang, out of doing functional differentiation like we just saw there. Okay. So any questions about that game? If not, let's do quantum mechanics first. Okay. So the story, the best way to tell the story is Tony Z has this quantum field theory book where he tells the story with its professor standing at the front of the class and Feynman in the audience, and you can guess what a joy Feynman must have been to be in the class. So imagine he's talking about the double slit. So you start off standard classroom lecture about double slits, that propagates from here to here, here to here, here's our screen, and you get interferences on that. Okay, so Feynman says, well, but professor, what would happen if you put another screen there? So you put another screen here and so the professor answers, of course, well, you'd go all different paths through the different screens. And he says, what if you put more holes there, professor? And so you put more holes in this thing, and you put little gaps there and there and there and there. And the professor says, well, of course, you'd go through all those different holes. And Feynman says, well, professor, what happens if you put an infinite number of holes and an infinite number of screens? And the professor takes his chalk and throws it at Feynman, of course. But, believe it or not, that's the actual derivation of the path integral. Basically, if you just go through that thought process and say that these things can go through an infinite number of screens along the way and go through an infinite number of holes in all those screens to get to the endpoint, then in fact that's what you mean by a path integral. You sum over all possible paths, and the only piece that you have to work on is what is the factor that gives you the phase of the wave function once you've gone through all those paths. Now when you're doing usual double slit, you do the free propagation, and that's basically what you do here. E to the I minus IHT for the different paths. So we'll do that. Okay, so we're going to do exactly that little story as the definition, as the derivation. Let's just do the setup though, because I have to tell you what it is we want to calculate. So we know that if you wanted to, end up at x f at some final time t, meaning you started off with some wave function at initial time t0, that you'd use e to the minus I h t minus t0 to get there. Okay, so this is some matrix somewhere. Okay. And actually, my original notation here is wrong. So I wrote x. That's psi final. Okay, so we have some initial wave function we're looking at a later time with some final state wave function. And here we can write it in terms of position wave function. So if I put in xf there, I put a complete set of states. Well, let's do it here. Let's do it the next line. I write integral dxf dxi of psi f of t xf e to the minus I h t minus t0 xi psi I of t0. Okay, so I've put complete sets of states, position states here and here. And that would be then written as the integral d3 xf d3 or dxf, 1 dimensions, 3 dimensions, it doesn't matter, dxi of psi f xf of t, something which we'll call dxf tf or t xi t0, and the initial wave function. Okay, so here's the and d is just this factor here, which is just right there. Okay, so our d, I'll suppress t0, but let's just write it as x, f, xi, and t is xf e to the minus I h t xi. All right, so this is just usual matrix element. I go through this intermediate steps of wave functions, and this is the beast I'm after. And this D really is the amplitude for starting at that point, ending at this point here, and in this screen's example would exactly be the sum over how many pathways through the screen. You just take the phase factor to get from one place to the next, presumably using plane waves, and that for that case of e to the IHT through the different paths. Okay, so here's then the derivation. Okay, I'm going to take that beast that's sitting at the top there and write it as a path integral. And you've probably, you very well may have seen this derivation, but I can't assume it, so I'm going to do it. I'll do it quickly, and it's your obligation to ask if you don't catch the subtle features. Okay, so basically what we're going to do is we're going to break it up into n time steps of delta t is overall t over n. So these are very small. And we're going to, at each stage, insert a complete set of states. Which would be, my nodes really do have D3, so I'll carry it along. It's 1 dimensions, 3 dimensions, whatever. So this complete set is like our infinite number of holes. You can be located at any location along in position space at a given time, and the delta t's are turned into the infinite number of screens. Okay. So for any n that's big enough that I can just take first order stuff, I can write d xf xi t as the integral dx1 up to dxn, so we've got n of them. Then we do xf e to the minus I h delta t, xi, well, let's make it xn here, xn e to the minus I h delta t, xn minus 1, etc., all the way down to x1 e to the minus I h delta t x initial. Okay. So there's this expression of a large number of screens, a large number of holes, and this is the factor that you have to calculate. Well, we can calculate that. So let's evaluate it. I'm going to take here, for now I'm just going to take h as p squared over 2m for now and evaluate it. And you'll see, if I add a potential, you'll see later on. It's real easy. Okay, so if I then have, some xi plus 1 e to the minus I p squared over 2m delta t xi, so one of those factors there, what you do is you insert a complete set of momentum states, dp over 2 pi cubed xi e minus I p squared over 2m delta t p x. These guys turn into, so one is I plus 1 and the other is I. So this guy turns into e to the I p dot xi. This p passes through there just because p squared over 2m. I get here e to the minus I p dot x minus I minus 1. Okay, and this started off being an operator, now it's just a number because it's acting on the p state, so it's just p. I then do the p integration, it's just the Fourier transform. And this then turns into, it's 2 pi I to the 3 halves. M over delta t to the 3 halves e to the I m xi minus xi plus 1 squared over delta t. Okay, so this thing that's an operator matrix element just turns into that number. And our overall answer, then we can write out the overall answer then. Okay, is this integral d3 x1 up to d3 xn. There's 2 pi I n over delta t to the 3 halves n, so there's a factor for each of those n integrations, and then e to the I, sum over all these i's, m over 2 xi plus 1 minus xi squared over, so let's put this over delta t squared and multiply by delta t. Okay, so I had 1 power of delta t. I've written as delta t squared and delta t there. And there's our path integral. Okay. we're going to group all these factors here. It's a bit funny because delta t is getting very small, but let's just do it. So you take the limit as n goes to infinity of this. This is then d of x is going to be defined as some normalization, which is that factor there, integral dx, which is all those integrations, and this is norm. It's not n, the number of steps. It's just some normalization, a number. And the piece up there, we're going to take as delta t goes to 0. This becomes the velocity, and the integral I delta t becomes the integral dt. So this becomes e to the integral I integral dt 1/2 m v squared. Okay. Okay, so there our path integral definition, and if I had added a potential, okay, I would have had e to the minus I h t is equal to e to the minus I p squared over 2m plus v t. V is just a function of x, and so it goes through this derivation unchanged, so it comes out as e to the minus I v. And so if I come back up here, this would be 1/2 mv squared minus v, which of course is the Lagrangian. So the momentum piece changed sign as you went through here. It started off as minus I p squared over 2m and ended up as plus I mv squared. The potential piece doesn't change sign, and we end up with a Lagrangian. Okay, so the phase factor is the integral of the Lagrangian. So there's your path integral. Okay. Let's quickly do some contents. That part I think you've most likely seen before. But I remind you that the contents of this is, one is the wave functions, and energies. So that if I define H some energy eigenstates, H n is equal to En, and I insert this complete set of states. So I've got D, XF, XI, and T. I started off, and leave a space there if you're taking notes, XF, e to the minus I HT, XI. Now I put in this complete set of states, energy states, N, and this then turns into En once it's sitting next to them. So I put it in here, it goes, makes H turn into En, and it sits there. There's then the sum over N, psi N of XF, that's actually psi star N of xi e to the minus I en t. So one of the standard tricks is you've defined this path integral up there. You solve that path integral in some way, and you look at the various pieces that go to like e to the minus I en t, and you pull it out. So if you've seen this in the quantum course, that's probably the next step. I'm going to skip over that. The other thing that you can get out of this is matrix elements. Okay. So if I wanted, so I've got xf, tf, xi, ti. If I wanted the average values of x at some t1, x at some t2 along the way, this in quantum mechanics isn't something you do very often, but you could ask the question, is the integral of this normalization dx x at t1, x at t2, e minus I ht. That's all that you do. Technically, this actually is time ordered. Okay, and the time ordering happens because you start over here in your initial state, you come along, and this propagation was ordered. So you put this ordered set of intermediate states there. So the early states have to things sit over here. For our case, this is just a function here. So these aren't really operators. These are just numbers at this stage. It's just something you're integrating over. But your usual interpretation of these things could, on that side, be operators if you wanted to. All right. So that's the path integral. Now we're very quickly going to move to just taking the ground state. So I'm going to project out the ground state. Okay. Functional methods almost always use the ground state. And the way you can get ground state matrix elements, you can sort of see from here. So what I'm going to do is I'm going to let the energy pick up a small imaginary component, and then take t goes to infinity, and then the only number that survives, if it has a small imaginary component, is the one with the smallest n, which is the ground state. Okay, so the typical trick is, if you want to get ground state matrix elements, you let the Hamiltonian turn to 1 minus I epsilon times the Hamiltonian. You take TF minus TI, and you call that tau, and that's taken towards infinity. And then when you have anything that you want here, so you've got sum over n, you've projected that out, e to the minus I en 1 minus I epsilon tau. Having put the I epsilon in with the right sign, you take this minus epsilon tau. This sum goes over to e to the minus I E0 plus things that are exponentially small. Okay. So that we have things like, so if I do that, I take dx f xi, t going to infinity is then this integral normalization dx e to the plus I integral dt prime, so minus infinity to infinity, of the Lagrangian with a 1 plus I epsilon. So it's the Lagrangian picks up a 1 plus I epsilon, roughly, and this turns into then psi 0 of x final, psi 0 x initial, e to the minus I e 0 tau, with tau going towards infinity. Okay. And so this lets you then take matrix elements in the ground state, all you're left with is the ground state. So if you want the ground state, so this is now ground state, time ordered xi of t, no, x of ti, sorry, x of tj, 0. You get that from taking the limit tau goes towards infinity of these matrix elements x initial, and then you divide out the wave function. So let's see, so I just divide out x f xi. And what we've done is we've derived the path integral representation for that. Actually, let me go back and just write that as dx, the normalization and all those integrals. So it's the integral dx x of t I x of tj e to the I dt of the Lagrangian over integral dx, the script d of x e to the I integral dt of the Lagrangian. All right, so we're whipping right along there, but that's our quantum mechanics. Okay, will I make it? Maybe I'll make it today. So if we're lucky, it looks like I may make it. I am pressing a little bit, so you have to slow me if you want me to say more. But my goal today is to take this for the harmonic oscillator and make this very explicit. I'll calculate x squared, the matrix element of x squared, in the ground state of the harmonic oscillator by these functional methods. We'll do this silly path integral explicitly and get a number out. Okay, so at this stage it looks pretty scary. Hopefully at the end it looks easier. Okay, ready to go on? If you're ready to go on, what I'm going to do is Nexus functional differentiation. Okay, so this I've set up that back when I was just doing those plain old numbers, if I wanted xj e to the I, well, actually, I don't need I for this guy. So I have sum over I of ji xi. Okay, so back when I was doing the example at the start of the class, I got those matrix elements, or that number, by taking d by dj sub j e to the sum over I ji xi. So somewhere in this sum, this is the summed index, there's the index j. When I differentiate with respect to that, I bring down a power of xj, and I get that identity. Okay. So I just want to do this, make a generalization of this to a continuum. Okay. So x at tj e to the I integral dt j of t x of t. Okay. So what we have now is not a sum, but we have this integral. But I want to write that in the same way as the derivative with respect to j. Okay. So, and actually, for this example again, let me take out the I just so I don't carry it around. We'll have I's in our final answer. But, okay. So if I wanted that, I'd like to define the functional derivative with respect to t sub j sub tj as e to the I integral dt j of t x of t. Okay. So that's in a sense our defining equation. You know, we want that. So then what does that really mean? Well, that's the formal definition then is that if I take delta of delta j of t acting on some j of t prime, that gives me delta of t minus t prime. Okay. Okay, so that implies then if I take delta of delta j of t on some integral dt prime j of t prime, some any function of t prime, then if I use that definition, then this becomes the integral dt prime delta of t minus t prime f of t prime, which is then just f of t. Okay. Okay. So this then this is functional differentiation. I have something that's a functional of j. Functional means that it involves j's at different times, different variables, lots of different variables integrated over. And if I want to differentiate that with respect to some external t sub j, I just differentiate using this trick. Okay, and it then just acts just like regular differentiation. Okay, cool. This lets us define the generating functional. So I'm going to define z, that's a z, sorry, z of j is defined as the limit tf minus ti goes to infinity of this path integral dx exponential I integral t initial t final. So those are going to be infinity dt. The Lagrangian, which is a function of x and x dot, plus j of t x of t. Okay, so there's the definition. And the use comes of this. So now this is a functional of j because it involves integrals over all these j's. But if I use functional differentiation, if I take derivatives let's take delta squared j of z of j delta j of t sub j delta j t sub I, and if I multiply by minus I squared just because I want to kill this fact, I do this, I'm going to get 2 factors of I kill that, is then the integral dx x of tj x of ti e to the I integral dt times that stuff again. Okay, so there are things like matrix elements that can be found. If I wanted 0 t x of tj x of ti, you put together all the stuff we've built up there. I take minus I squared, I differentiate z with respect to j ti tf j of ti. I get that. I divide. At the end of that said j is equal to 0, and divide by 1 over z of 0 cancels out all those normalization factors. And so there's matrix elements. Give me a Lagrangian. This is the ground state matrix elements for that Lagrangian. Okay, and the most obvious ones that we're going to do is I'll take this and I'll let TF goes to TI in our examples. Okay, so that just gives me the ground state matrix element of x squared. And your homework will consist of doing excited state matrix elements. So not just the ground state. From the same functional, the same tricks, you can get the excited state matrix elements also. So it contains, in principle, it contains everything about your system giving you a Lagrangian. Okay? Yeah, everyone with me? Or maybe you don't believe me, but you're with me, huh? So, if you're at least with me, I'm going to do the harmonic oscillator now, and I think I have about the right amount of time. Okay. The technique for the harmonic oscillator is almost exact parallel to doing field theory. I'll do it in 1D just for notational simplicity. And the trick that I have for this minus I epsilon trick can be taken by, if I have omega squared in the harmonic oscillator, take it to omega squared minus I epsilon. That's like the 1 minus I epsilon h trick. And actually that's going to play a role. Actually you'll see the I epsilon appear in the calculation, because we'll need that to do something, do a contour integral along the way. So the action, which is the integral of the Lagrangian, which sits in the exponent there, is 1/2 m x dot squared minus v, which is m omega squared x squared. And then I'm going to add this j of t x of t source, because I want to do that in the functional integral. Okay. If I rewrite this, I'm going to rewrite this in the following way. dt. So I've got x dot there. I take one of the x dots and I integrate it by parts and put it on the other one. So integrating by parts gives me 1/2 m x. Then I put brackets there, d by dt squared, and brackets here, x. So instead of having x dot times x dot, I have a second derivative on one of them. It could be acting either to the left or the right. It doesn't make any difference which way it acts. But the advantage of doing this is then I get plus omega squared as the potential piece. Yeah, so there's x, d squared plus omega squared x is the Lagrangian part. And then I have the plus j x piece sitting there. Okay. So in our exponent we have this here. Now the integrals that I started path integrals with were sort of like this. Instead of a continuous variable t, I had a summation xi and xj, and I had a matrix aij. So previously, let's write it over here, I had x dot a dot x plus j dot x. Okay. That's sort of like this. If you go back and make these discrete, this is like the j dot x, and this is like this matrix x a j, and I solve that using this Gaussian integration, and I ended up with things at the end that look like j a minus 1 j. And that's going to be the same thing here. We're going to end up with a j a minus 1 j. This is a, and a minus 1 will be a propagator. Okay, be a Green's function, the inverse of that. Okay, so let's just do the calculation. I'm going to do the calculation by completing the square. Okay, I've got x squared and x, so I can complete the square, but x squared has this funny differential operator. So let's define the inverse of that. So basically, my differential operator is d squared by dt squared plus omega squared. The inverse of that is what I'm going to call d of t minus t prime, and up to a minus sign, it's delta function of t minus t prime. That's what we mean by the inverse. Okay, so let's just define that. Well, that's pretty easy to calculate. I'll give it to you a little further down the road. Just carry it along. But then completing the square, I'm going to define x twiddle of t is x of t plus 1 over m integral dt prime d t minus t prime j. Okay. Right. If you do that, then so this is if I take this differential operator d squared by dt squared plus omega squared acting on this x twiddle, it's the same thing acting on x. And then the piece that where it acts here gives me minus 1 over m j of t. Okay? So that's useful. Then if I had this thing being x twiddle instead of x, the differential operator gives me the x piece, and then there's a minus sign that cancels the j piece. Okay, so let's just write out that again. So F, the action that we had there before, can be written in terms of dt minus 1/2 m x twiddle d by dt squared plus omega squared x twiddle. Okay. So if I do that, I get the x pieces unchanged. I get the j dot x pieces here from just doing this. Okay. So the j dot x pieces come out unchanged. But now I have a quadratic piece left over, which is this term with this differential operator, the product of two j's. Okay, that guy works out to be minus 1 over 2m integral dt prime j of t d of t minus t prime j of t prime. Okay, you see that? All right, if you want me to step through it a little bit. So there's integral dt dj twice with one of these differential operators there. That differential operator acts on one of the d's, makes that a delta function. And so you have two j's, 1d left over, which is this guy. Okay, again, I'm pushing it a little bit, but not too much, I hope. If you want to ask, please ask. Okay. So this tells me, so that our path integral that we had was the integral with that term in the exponent. So now let's just write it out then. So then the path integral was, or the generating function, z of j, was the integral d of x e to the I s, that was a function of x and j, okay. This is the s with a variable x twiddle and j set equal to 0. Okay, so that part by itself. So this is the integral d x e to the I s x twiddle j set equal to 0. And then the second piece is e to the minus 1 over 2m integral j dj. That's this term right there. I don't have space to write out all the indices. Okay, at this stage you play the usual path integral trick and say that the integral over all x is the integral over all x twiddles. They're just shifted by a number. So that this generating functional is that with j is equal to 0. And here I will write out all the indices. Minus I over 2m integral dt prime j of t d of t minus t prime j t prime. Okay, so we've done the bloody path integral. You know, the only thing we had to know about is that it's integral over all paths. And now it's gone. There's no more, this is just a usual function that you're used to, and we've gotten rid of it. So it's not quite as scary as you want. So a calculation then would be, now, if I wanted 0, so again, time ordered x of t1, x of t2. 0 is I minus I over minus I squared, 1 over z0, del squared d j of x1 delta j of x2 z of j. So we pushed all this into this functional, and we said j is equal to 0 at the end of that. Okay, so from what I've done before, you can read off the answer. Okay, so z of 0 is going to just drop out. It sits there and it sits there, it just drops out. By differentiating this once with respect to j, I bring it down to d. Another j. I differentiate a second time. I cancel the other j, and I'm just left with a d. If you can do that in your head, we're good. If you want me to do it in more detail, I can do it. This becomes then minus I squared minus I over 2m d of t2 minus t1. And then something that of real interest, it would be the ground state expectation value of x squared is then the limit of t2 goes to t1. And actually I have a mistake there. Sorry if you're, there's no 2. Let me just finish writing this equation. I over m d t2 minus t1. Okay, why was there no j, no 2? Because when I take that first differentiation with respect to j, there's 2 j's I could differentiate, either this one or that one. It cancels that factor of 2. So we get for doing it in our heads. Okay, so if I want this expectation value, I have to calculate d in that limit. Okay. So to evaluate this, okay, I'll claim that d of t minus t prime is the integral dE over 2 pi 1 over e squared minus omega squared plus I epsilon e to the minus I e t minus t prime. Okay, this is just a Fourier representation of that, because you can just see it if I do it. D squared by dt squared plus omega squared d is, well, the t dependence is explicit, so I get dE over 2 pi minus e squared plus omega squared, or there's no more pole once I do that. And that's the delta function. So it works. So very quickly, there's D. At this stage, I've added the I epsilon there because I go back to my start of the harmonic oscillator. My convergence factor is taking omega goes to omega minus I epsilon to make things converge. And so that's why I put the minus omega plus I epsilon there. Okay? Then so the I epsilon was for convergence. Which, in a sense, well, it comes from the fact that I want the times to run the right way. The time ordering is important, causality. But then, given that I can do the contour integral, do it by contour integral. Okay, and you get d of t minus t prime is minus I over 2 omega e to the minus I omega t prime minus t. That's absolute value sitting there. Okay, and now you can. I've done enough of these probably. You can do this when t is bigger than t prime. You close the contour in the lower half plane, I guess it is. You pick out the pole, and you get at the pole you get the residue being 2 omega. So the usual tricks there. Okay. So with that, then we get 0x squared 0 is 1 over 2m omega. Okay, and well, I have the usual one with creation and annihilation operators to work out, but I'll skip it just because of the time. We've got a number. So this is probably the most painful way to do the harmonic oscillator ever. Barry Holstein and I used to always joke that we're going to write this book, 101 ways to solve the harmonic oscillator. And you start off with, freshman mechanics with a little forces minus kx. And this is going to be the last one. This is the 101th way to solve the harmonic oscillator. And in your homework, you'll then get other matrix elements of the harmonic oscillator by this incredibly roundabout way. But the nice thing about it, so it's a painful way to solve the harmonic oscillator. It is, however, what we do in field theory. So all the steps that we did here, these picking out the ground state, doing the Green's functions, all that stuff is replicated exactly in field theory. And it does give you the sense of that you can make this abstracting, this path integral, into something very concrete. You can, on this page here, all we've got are just usual integrals, real numbers that we're familiar with, where we started out with this seemingly ill-defined integral over all paths. Okay, so let's stop there. Next time I come back and I transition into path integral field theory, and we do a couple tricks there to get out Feynman rules by path integrals. Okay, good. See you next time.